Hi guys, Rod from Bensonian Thought Videos here, and this is the 6th video in my series examining the underlying philosophy that gives rise to the scientific method. So we are now into our 3rd week of mathematics. We shall start this week by proving Pythagoras' theorem, as we need this to work towards proving Einstein's famous equation E=mc squared. We have already introduced some basic geometry around angles, so let's continue to explore angles and create two basic shapes, a triangle and a rectangle. We have already defined the area of a rectangle as just its length multiplied by its height. Therefore, if we now draw a diagonal line through a rectangle from corner to corner, we divide the shape into two equal right-angled triangles. Therefore, the area of a right-angled triangle is just half the base of the triangle times its perpendicular height, as shown in the figure. This formula also works for all triangles which don't have a right angle in them, but we do not need to prove that for our proof of Pythagoras' theorem. Now let's take a look at the following two line intersections which form four angles. It is easy to show the opposite angles are equal as follows. From the above diagram, it is clear that A plus B plus C plus D equals the sum of a full circle, which equals 360 degrees. Likewise, A plus B equals 180 degrees, it's a half circle or straight line. C plus D equals 180 degrees, again a half circle or straight line. A plus C equals 180 degrees, and finally B plus D equals 180 degrees. Thus, C plus D must equal A plus C, and so D equals A. Likewise, B plus D equals C plus D, so B equals C. It is these types of relationships which become the building blocks of geometry and geometric functions. Now we move on to proving that B equals C in the following diagram on the screen. We start by recognizing that angle B must equal angle A because the two horizontal lines are parallel. This is not a theorem but a postulate in that we don't prove it but rather state it must be so, as this is really what it means for the two horizontal lines to be parallel. Another way to convince yourself that this is true is to start with two intersecting lines. In this case, we have only a single angle B. Now, if one imagines splitting the horizontal line in half along its length and then moving the two resulting lines apart, the figure on the screen will result, with angle A being angle B translated vertically by the distance between the two parallel lines. We have already shown that opposite angles of two intersecting lines are equal, so therefore C equals A, and so C also equals B. Now consider the triangle on the screen. Using what we have just proved, that the opposite angles of a line that intersect two parallel lines are equal, we can easily show that in the figure, angle lowercase a equals angle capital A, and angle lowercase c equals angle capital C. Now, since lowercase a plus b plus c equals 180 degrees, as this is just the angle of the straight line OP, then uppercase A plus lowercase b plus uppercase c also equals 180 degrees, which of course corresponds to the internal angles of the triangle shown. Let's now explore the geometrical properties of our triangle a bit further. So firstly, the order of the three internal angles inside the triangle are irrelevant in that every angle is adjacent to any other angle. This means that if we have two triangles with angles ABC and BCA, as shown in the figure, we can rotate and sometimes, if necessary, flip the second triangle so that the angles match up. It should be noted that if you have two triangles with two internal angles that are equal, then because the sum of the internal angles must sum to 180 degrees, all three angles of the triangles are equal. The next step is to explore how the internal angles of the triangle affect its side lengths, as now shown on the screen. From our exploration of side lengths, and internal angles, it is clear that the internal angles control the side lengths relative to each other. This means that two triangles with the same internal angles must have side lengths that are in the same ratio. This is just observed to be true, and therefore forms what is known as the angle-angle-angle postulate of similar triangles. It also means that two similar triangles can be made identical simply by scaling one triangle into the other as shown. Therefore, if two triangles share all the same internal angles and a common side length, then the two triangles must be identical, because the shared side length means the triangle scaling factors are identical and the side ratios all match by virtue of the triangles all having identical internal angles. Now consider the right angle triangle on the screen. Pythagoras' theorem states that a squared plus b squared equals h squared. We prove this using the following figure. This figure is simply one large green square with a second smaller blue square inside it, placed in such a way that we make four right angle triangles, now coloured green, and labelled 1 to 4. Given we have two squares, we can identify all the angles that are 90 degrees as shown. For triangles 1 and 2, we shall label their internal angles as alpha, beta for triangle 1, and x and y for triangle 2. Now starting with triangle 1, it is clear that alpha plus beta plus 90 must equal 180 degrees, as this is the sum of the internal angles of a triangle that we just proved earlier. Likewise, we can see that beta plus 90 plus x must also equal 180 degrees, as this is just the straight line of the top edge of the big green square. If we now subtract equation 2 from equation 1, we are simply left with alpha minus x equals 0, and so alpha equals x. We now replace our x label with alpha, and now note that the sum of the internal angles of triangle 2 must equal the sum of the internal angles of triangle 1, and so alpha plus 90 plus beta equals alpha plus 90 plus y. Subtracting 90 and alpha from both sides, we are just left with y equals beta. Now all four triangles share the hypotenuse of h, as this is the side length of our smaller blue square. So triangles 1 and 2 are identical by our angle-angle-angle side postulate for determining identical triangles that we just learnt about earlier. We can repeat this process for triangles 3 and 4, and so demonstrate we have four identical triangles. If we now finish labelling all our triangles, identifying their other sides by the letters A and B, we are left with the figure that is now shown on the screen. Okay, so here comes the algebra. The area of the single triangle is just half its base times its perpendicular height, which in this case is simply a half AB. Thus, the area of the four triangles is 4 times a half AB, which equals 2AB. Now the area of the big square equals a plus b all squared. We now need to expand a plus b all squared. Last week we broke this down by letting a plus b equal k and did the expansion in 2 steps by first calculating k open brackets a plus b and then replacing k with the answer a plus b. This week we shall do away with the k and write our first step as open brackets a plus b close brackets a plus open brackets a plus b close brackets b. This results in the basic rule that every term inside the first bracket must be multiplied by every term inside the second bracket. So we get a times a plus b times a plus a times b plus b times b. But a times b is the same, of course, as b times a, so we end up with a squared plus 2ab plus b squared. Now the area of the little square is just h squared, but the area of our four triangles can also be found by simply subtracting the area of the small blue square from our green square. This difference is therefore a squared plus 2ab plus b squared minus h squared, and this area must equal the other way of calculating the area of our four rectangles, which was found to be 2ab. So we end up with 2ab equaling a squared plus 2ab plus b squared minus h squared. If we subtract 2ab from each side, we end up with 0 equals a squared plus b squared minus h squared. Adding h squared to both sides of this equation, and we end up with h squared equals a squared plus b squared, which is Pythagoras' theorem. So we have done it. We are one step closer from proving Einstein's famous energy formula for matter, which is E equals mc squared. The next mathematical tool we need is calculus, but this is a very big subject and requires at least one separate video, possibly two. However, before I close this video, I have decided to add one more bit of maths, which is not necessary at all for deriving E equals mc squared, so feel free to skip the rest of this video if you want. This final section, if we are using my skiing analogy, is like me taking you off-piste for a bit, just to appreciate some pretty mathematical scenery, and that is the birth of the irrational number. So in my first maths video, I was developing the number system, and I briefly mentioned that there exist numbers which cannot be fully written down, and we call those irrational numbers. Interestingly, the first irrational number to be discovered was root 2, and unsurprisingly, it pops up straight out of Pythagoras' theorem when we try to calculate the rather innocent-looking hypotenuse length of a triangle that has a base and a height length of 1 unit, as now shown on the screen. Proving root 2 is irrational beautifully demonstrates the power of using our zeroth axiom of coherency as a test of truth. So you'll remember in our first video we spoke about how we can code fractions in decimal notation. Now of course we can make the denominator of a fraction as large as we like, so it is tempting to think that any number should be able to be captured as a fraction, because we can make smaller and smaller fractions just by increasing the denominator, and so in theory we can get a number as precise as we want it. For example, on the screen we have a very large number over another very large number, which gives the fraction 0.1923045967523456540394. Yet we cannot write root 2 as a fraction, as the decimal numbers go on forever. On the screen we have the value of root 2 to the first 10,000 decimal places, but as I said, the decimal number goes on forever, which is why you can't ever get to the end of it to write it down as a fraction. We are now, with some basic algebra, going to prove that root 2 cannot be expressed as a fraction. We are going to do this by making use of a technique called proof by contradiction. We will assume that root 2 can be written down as a fraction, and then do some algebra which will show that if this was the case, we would get a fraction which does not actually exist. So before we start, how can a fraction not exist, I hear you ask? Okay, let's think about zombies for a moment. Do they really exist? Well, no, they don't. But of course, if I Google zombie and click on images, I can get plenty of pictures of zombies. Of course, we all know that our zombie pictures are just normal people dressed up to look like zombies. Well, believe it or not, fractions can also play a little dressing up game. For example, the fraction 8 over 12 is a fraction in disguise. You see, I can immediately factor out 4 from both the denominator and the numerator to get 2/3. So really, the fraction 8/12 is just 2/3 wearing a disguise, so to speak. Now, with a little thought, it should become obvious that all fractions with an even number in both their numerator and denominator can be simplified by factoring out 2. Again, take the fraction 2 over 4. We divide the numerator and denominator by 2 over 2 to get back to the true fraction of a half. This means that all fractions, when in their simplest form, must have an odd number in either their numerator or denominator. If they have an even number in both, then they are simply not fully factored out, and so can be further simplified by dividing them by 2 over 2. So what we are going to do now is pretend that we can write root 2 as a fraction, and we shall call this fraction a over b. So we now have a over b equals root 2. We square both sides and get a squared over b squared equals 2. So a squared equals 2b squared. Okay, what next? Well, we are now going to create two functions. One that spits out all even numbers and the other that spits out all odd numbers. The function e equals 2n spits out even numbers, i.e. 2 times 0 is 0. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, and so on. So it's spitting out 2, 4, 6, 8, all the even numbers. To get an odd number function, we simply add 1 to our even number function. So we have O equals 2n plus 1, which gives all the odd numbers. 2 times 0 plus 1 is 1. 2 times 1 plus 1 equals 3. 2 times 2 plus 1 equals 5. 2 times 3 plus 1 equals 7, and so on. We are now going to square our even number function. E squared is simply equal to 4n squared. Okay, so let's now let x equal 2n squared. We put x back into our e squared equation and we get e squared equals 2x. So this means that the square of an even number is an even number. What about our odd numbered function? Well, o squared equals 2n plus 1 all squared. Working through the algebra term by term, we get 2n times 2n plus 2n times 1 plus 1 times 2n plus 1 times 1, which equals 4n squared plus 4n plus 1. Or, to write it another way, 2 open brackets 2n squared plus 2n close brackets plus 1. Once again, we shall now let x this time equal 2n squared plus 2n. Putting this back into our answer, we get 2x plus 1. This is just our odd number function again. So this means that the square of an even number gives an even number, while the square of an odd number gives an odd number. Thus, it is impossible to square root an even number and get an odd number, as all odd numbers square to an odd number and all even numbers square to an even number. So returning to our algebra above, we have a squared equals 2b squared. But 2b squared is an even number, which means its square root must also be an even number. So what we are going to do is now replace our a with the even number function 2n. We thus get open brackets 2n all squared equals 2b squared, which becomes 4n squared equals 2b squared. So dividing both sides by 2, we get b squared equals 2n squared. But by the exact same reasoning above, this means that b must also be an even number. So if root 2 could be written as a fraction a over b, then both the numerator and the denominator would have to be even numbers. Yet fractions with both even numerators and denominators don't actually exist, because they are just fractions with an odd number in them that have not been fully factorized. And so we have proved that root 2 cannot exist as a fraction, and so its decimal expression must be non-repeating and go on forever. Now you might think that the first person who made this amazing discovery would be feeling happy about it, and their genius would be hailed by their contemporaries. Not so. Legend has it that the first person to discover this amazing truth was the Pythagorean philosopher Hippias in the 5th century BC. It is said that his contemporaries were so incensed at his discovery, especially since it went against their great founder Pythagoras himself, that they drowned the poor man at sea. One modern writer even suggests it was Pythagoras himself who did the deed. If the legend is true, then poor old Hippias really was two-rooted. All I can say is how little the academic world has changed. Now, perhaps the response of Hippias' colleagues to his amazing finding further demonstrates our subconscious disliking or our inability to understand the infinite. Anyway, enough playing around with off-piste mathematical skiing. Next week we shall resume our quest up the mountain to prove E equals mc squared. In the meantime, if you like this video, please do hit the like key, and if you want to see more of my content, then please do subscribe to my channel by hitting the subscribe button and the bell notification key below. Until next time, I hope your body and mind are in a good place, and bye for now.